Alright class, let's continue. So in the next 30-40 minutes of this lecture, we're going to discuss how we can use root locus to help us do control design. Of course, in this part when we do control design, since we have discussed various things from chapter 4, how to design controller to satisfy given transient performance, transient specifications. Chapter 7 we discussed how to design controller, choose parameters such that you will have you can achieve certain requirements with respect to steady state tracking errors. And lastly, in chapter 7 and now in chapter 8, locus, we have seen how we can choose this undetermined parameter k such that we can achieve stability. And now we're going to combine all things together and see how we can do the control design in a more integral manner. Now, the control design that we're discussing here are based on the approach that focus on the performance of the system in the time domain. Or time domain approach, maybe. Time domain approach. Right, because when we talk about steady state, we're looking at this one. You know, it's in the time domain, right? It's t to infinity. You have time argument t. Or if you talk about, let's say, we'll talk about overshoot, or we talk about settling time, rise time. Those are all the behavior or performance of a control system in the time domain. In the next chapter, we're going to discuss how we can approach control design from the frequency domain. Meaning we're going to look at the frequency response function, transfer function, and discuss how to do the control design. And we'll do this through an examples throughout this chapter. Now, as far as controllers are concerned, we actually discussed this in the previous chapter. We're looking at, the main commonly used types of controllers. We're going to look at P control, proportional control, PI, PD, and PID. So these will be the controller types of controllers we'll focus on. And you can, as I mentioned, there could be, infinite number of possible ways to design a controller, to construct a controller, or to construct the transfer function of controller, but these are the most commonly used ones in practice, and will be the ones that we'll focus on. So this is what we're going to do. Let's look at an example. And we're given the transfer function, open loop transfer function. No finite zeros to finite poles. And the goal is to have the closed loop system track the reference input, a step input, with 10%, less than 10% of steady state tracking error. This is 2 unit step input. In addition, we want the percentage of overshoot to unit step input to be less than 5% in transient, and I want the rise time to be less than 0.8 seconds. Okay, I want all three goals to be satisfied simultaneously by apply a feedback controller in the following manner. And just for simplicity, let's assume the plant as the transfer function directly, and the output of the plant is directly fed back to be compared with the reference R here, and this is my output Y. So this is my goal. I have a system of a plant. I want to apply a controller such that steady state tracking error to unit step input is less than 10%, and during the transient the overshoot is not going to exceed 5%, and the rise time is less than 0.8 seconds. And we'll try P control. So in this case, the transfer function of the controller is K, right? And we can say the closed loop transfer function will be equal to, and we have done this multiple times, 4K divided by S plus 2, S plus 3, plus 4. Okay. Since now K will be a controller. Or this, you can write it as plus 5S plus 6 plus 4K. This will be our closed loop transfer function. Now let's first have a look at the rule locus, since when the controller is K, is just naturally what the scenario we discussed earlier. So this is the real axis, this is the imaginary axis. You have two poles, -1, -2, 1, -3 second. And the sections on the real axis will be right here, right? Since on the right hand side of this section you have one pole. And the asymptotes will appear here, and the asymptotes you should have two, with the angle being 90 degrees and minus 90 degrees, since the difference of the order here is just 4 on top and the second order polynomial in the transfer function. Okay. And compare here, order being 0 for the polynomial of S, and here there's a second order polynomial. So we have that, and the centroid will be -2, -3, the sum of your open loop poles. I don't have any open loop 0, so I don't have to do anything, divided by 2, so -2.5. Right in the middle. Now, and we have discussed, well, since it started from the poles, the two branches of locus should move towards each other and will break away. The breakaway angle will be 90 degrees since you have exactly two poles involved. The breakaway point can be calculated using the method we discussed earlier. Okay. And the method we discussed earlier says the following. You can use one of the methods, right? You do the summation of this 1 over all the poles, and that will give you what? That will give you 1 over S plus 2 plus 1 over S plus 3, equal on the right hand side of 2 is 1 divided by s plus or s minus all the zeros. We don't have anything that. Just put a 0 on the other side. And maybe let me complete this. So this will be s plus 2, s plus 3, and on top I have 2s plus 5 equal to 0, or s equal to 2.5. So, sorry, negative 2.5. And this negative 2.5 is exactly your breakaway point. Right here. And if you look at this, the negative 2.5, the breakaway point happens to be exactly equal to the centroid. And the breakaway angle is 90 degrees, also the same as the angle of your asymptotes. So this is what the breakaway will look like. They will break away, they'll come together, and when they break away, they will break away up and down exactly, hold that 90-degree angle, and goes towards infinity. And this will be the root locus of a closed loop system with the plane defined in the highlighted area and with the controller being a pure P controller. Now, we want the overshoot to be 5%, right? This is what we want. Now, if we plug in this 5% overshoot into the equation we have, and we'll find out the following. Okay. Usually when you plug in the equation into, plug this 5% into the equation we have used in chapter 4, you should be able to find out, well, the corresponding damping ratio to this 5% number is roughly 0.6901. Well, in control design, what we will do is we do approximations a lot when we do the initial design. So we'll say, well, if 0.69 will give you 5%, I'll give it a little more cushion, a margin, such that I will make it equal to square root of 1/2, or square root of 2 divided by 2, which is approximately 0.7071. So slightly more damping supposedly should give you even more suppressing to the transient, and the resulting overshoot from this is about 4.32%. Okay, and which is a pretty good number. So you want it to be less than 5%. I'll give it 4.32. And this is convenient because remember this zeta is a cosine of an angle, and cosine of square root of 2 over 2 is actually 45 degrees. So when you ask for 5% overshoot in control design, what we usually do is, well, we'll find this 45 degrees. And cosine 45 degrees is equal to square root of 2 over 2, or 1 divided by square root of 2. and this will be the zeta we're looking at. The zeta we're looking at. And we discussed this also in chapter 4, right? If you want this kind of overshoot, you should search for roots along this direction, and you actually find out where they are on the root locus. These are the two red dots I have here and here are actually the closed loop poles that can give you this 5% overshoot or 4.3% overshoot that you're looking at. So this means the closed loop poles will be negative 2.5, since this is where the asymptotes and the breakaway point is, and since it's 45 degrees, the real part and the imaginary part should be exactly equal to each other. So you have the two closed loop poles. Okay? So this is how we can satisfy one of the requirement that this 5% overshoot is done, we actually can achieve 4.3%. Now let's just check the others. Are you able to achieve the steady state tracking error to be less than 0.1? Well, we can find out. We did this in chapter 4. And how we actually do that? And we do this through the following. First of all, if you want to calculate, you need to know what is the k involved. Right? K is the constant such that you will actually reach this. So this means we're going to have the k to be calculated. And what you can do is you can utilize this equation again, this characteristic polynomial again, right? We use it multiple times, so k should be equal to negative 1 over gh, or in this